Hello, welcome back. You're watching Code Dive, and well, it's time for our next speaker. And our next speaker is Agata Migalska. Now, Agata is a data scientist with a strong background in computer science research and software engineering. She currently works at Nokia and applies statistical and machine learning methods to support business processes. In the past, she worked on large enterprise systems, e-commerce solutions, image processing, optimization, and human-computer interaction. Now, on the side, Agata has been contributing to an international research project that is focused on the modeling on the coronavirus spread. So, Agata, thank you very much for this contribution. And, well, yes, talk to us about your supply chain profitability.
Thank you for this lovely introduction. Welcome, everyone. Today, I'm going to talk to you about cloud business solution, increasing supply chain profitability. So, you already know a little bit about myself. From my background, I'm a computer scientist. I've been working quite a long time in software engineering. And also, as was said, I'm contributing in my free time to the modeling of a coronavirus spread research. Today, we're going to talk about this supply chain and optimization within it. And so first, I will present to you the motivation and the problem. Then we'll go into the solutions that can be applied to these kind of problems. And that calls upon reminding you what a prescriptive analytics is and what optimization is about. Then we'll get into the optimization engine itself, like how it was implemented and what kind of problems it can solve. Then the second part of the presentation is going to be focused on embedding the solution in the cloud. And that will also reveal some challenges that we faced when doing this embedding. So that will be covered in the automation part. And finally, I will summarize my presentation. So in a nutshell, the presentation is going to be from the problem through the algorithm that was developed to the whole infrastructure in which this algorithm was embedded. So this is the general overview of what I will be presenting to you today. Okay, let's start with a motivation and a problem statement. From time to time, the component market is observing some sort of component shortages. So all the companies that are within the electronic market are suffering due to this component shortage. And the component shortage can arise for two reasons. It's either due to the abrupt rise in demand, or on the other hand, it can be a sudden drop in supply. And the reason why the companies suffer from this component shortage is that they actually cannot provide enough products to their customers, and so it is connected to the risk of missing the revenue or terms and conditions that require some penalties. And at Nokia, we noticed that the tools that were available in the market, the commercial tools, are not sufficient to give us enough power or possibilities to perform the systematic and analytical optimization process of these components allocation in a situation of a component shortage. And also what was noticed that there is a limited possibility provided by these tools to simulate the situation when you don't get the components from your suppliers, but these components are available in a market. So you can just go and kind of purchase like you would go into the shop and buy these components. And there was no way to decide whether this kind of decision pays off. And the solution that we proposed is the optimization program, which is actually integer linear optimization program, that is allowing for systematic allocation of such components to products and then to customers. As a side effect or side benefit of a solution that we provided is that we integrated the data coming from various sources, from the supply, from demand, from commercial, meaning prices and terms and conditions. And it was already giving our stakeholders the overview of the supply chain process. To give you an idea how big the supply chain optimization problem is, here is a diagram that basically explains it. These numbers are arbitrary, but what we have is there's some number of suppliers who are producing or delivering some components to our factories. These factories are then in turn manufacturing or assembling sales items. Sales item is a product, this is equivalent, and these sales items are then delivered to customers. And if we just look at the numbers here, that gives us quite a lot of combinations. So imagine that there is some component missing, and now decide which factory does not get these components to assemble products, decide which products do not get produced, and decide which customers do not get their products. So this is basically beyond human capability to solve this problem by hand, and this is the reason why we need more advanced analytical tools. And that way, let us go into business analytics and specifically into prescriptive analytics. So business analytics is about designing models and simulations that allow to create scenarios, understand reality, and predict the future. What is important about these tools is that they are not only models. These models are put into a larger software that is able to produce insights, that is embedded in applications, and is then generating some outcomes that can be used by business stakeholders. And within business analytics, we can distinguish 3 building blocks. First of all, we have descriptive analytics, which allows us to answer the question, what happened and why did it happen? So basically, we get some insights from historical data. Secondly, we can have predictive analytics. So we can predict what will happen. And so it gives us some future estimates. And finally, we have prescriptive analytics, which answers the question, what shall we do to achieve certain goal, to make something happen? And so this is a decision recommendation that we are obtaining out of this process. So what we're going to talk about today is basically about decision support systems. And there's quite a few ways to approach decision making. So first of all, you can have an expert system. An expert system is basically when you put all the expert knowledge in kind of a box, and then when you're dealing with a problem that is applicable to this expert, you just kind of write it down and ask this expert system to give you the recommendation, what shall you do? And this is one of the oldest approaches to artificial intelligence and for the intelligent decision making. And it was motivated by the fact that expert knowledge was, there were not many experts, so the knowledge was scarce, and there was a huge demand for this kind of knowledge. Then we have fuzzy logic. Fuzzy logic is a system where you, well, is it hot or cold today? It's kind of hot. So fuzzy logic captures all this kind of. So it has all these flavors of uncertainty that we humans express. And then we have multi-agent systems and microsimulations. And these are very interesting systems because, well, you have a bunch of agents. Each agent is a rational individual. So it has some rules implemented or some general logic towards its behavior implemented. And then you just put the whole society of such agents in some circumstances, and you observe how they interact and what is the outcome of this interaction. So basically, you can apply certain changes to the environment and then see what is the outcome over time. So multi-agent systems are great for observing how the society will evolve. And one very interesting system, although it is not directly connected to decision support, is Massive. Massive was developed for Lord of the Rings in early 2000, years 2000. And basically each warrior is an intelligent agent that is governed by these fuzzy logic principles. And then you have a whole battlefield of these agents. And you can observe some, well, basically rational behaviors, like somebody fleeing from the battlefield and other interactions of these warriors. Then let's jump back into decision support systems from this Massive. And so here another way to approach it is artificial neural network. And so basically you have some sort of black box where you put some inputs and you get the output as a decision. You might not understand why this decision was taken, but apparently it's an optimal decision. Further, we have reinforcement learning. And so here we want to know the sequence of actions that we should perform in order to achieve certain goals. So reinforcement learning is currently very much used for playing games. So you want to win a game and then you need to make certain steps to actually win it. And finally, we have optimization. And this is going to be something that I'm going to talk about today. And optimization is actually not a new concept. It was developed in the 50s of the previous century. And for that reason, it is maybe not the sexiest as the neural networks are at the moment. But on the other hand, there is still an ongoing research into providing new techniques for optimization. There's a lot of research towards using GPU for optimization, and so on. And also due to the capacity of our computers, the size of the optimization problems we can solve is getting bigger and bigger. Okay, so I discussed these optimization problems and the decision support systems for a while now. We know that we're going to talk about optimization, so let us have a feeling for it. So for instance, an example optimization problem might be that you are going on a 2-week quarantine and you want to buy enough food to be able to compose diversified meals because you don't want to eat spaghetti every single day. And so you want some sort of composable meals, and then you also don't want to exceed the budget. So in principle, you have some food items, let's call them food items for no better word, and they need to be composable into meals. And you have these two constraints of the money and the time. So in optimization, we always need to describe 3 things. One is an objective function, so what it is that we want to optimize. So in this case, we want to maximize the diversity of our meals. And secondly, we have some decision variables, so something that we can change. Here we have a quantity of these food items, or actually quantity of each food item. So if you make a list of all the food items that there are in a supermarket, you kind of can assign the quantity of each of them that you want to purchase. And finally, we have constraints. These constraints are, in this case, that we don't want to exceed the budget that we have for the food. We want to make be able to make at least the number of meals that we want to make should be enough for 2 weeks. And also these food items that we buy must be composable into meals. So this is one simple example that you might be dealing with on an everyday basis. You might be saying that, oh, I'm not going on a quarantine anytime soon. At least I hope I'm not going on a quarantine anytime soon. But then if you think of a kind of normal life that we used to have a year ago, you might have been going to work from Monday to Friday and then on Saturday doing the shopping for the whole week. And this is basically a very similar problem. Another problem that you might be facing in your everyday life is about routing. So basically, you want to go from point A to point B and visit some places on your path, on your route. So you're starting with a dot here at the top, and you want to get home, which is on the right. And then on your way, you want to visit a cafe, a bank, and a shopping center. And now the question is, which path is optimal if you want to have a fastest route? So like, in what sequence shall you go to these points to get the fastest route? And so again, if we want to express it in these three elements that are important for optimization, first of all, we have an objective that we want to maximize the time spent, time spent commuting. Second of all, we have these variables. First of all, the sequence of stop points. And second of all, we might want to use different means of transport. So we might also want to consider that. And the constraint is that each point should be visited exactly once. So now I believe you have a pretty good understanding of what optimization problems are about. And so let's dive into the optimization engine that we proposed in our solution. So going back into supply chain, we have these suppliers, we have products, and we have customers. Customers give us a demand for the products. And now the whole thing about the problem that we are dealing with in here is to answer simultaneously two questions. How to allocate components to products, and at the same time, how to allocate products to customers. And remember, we are facing the situation when there is a component shortage. So we don't have enough components to produce all products and satisfy all the customers. We need to harm somebody, and the decision here is about whom. And let's now jump into the definition of a problem. There's going to be some math, but don't get scared. It's just a little bit, and it will be, well, explained. So first of all, we start with input variables, and there is first of all bill of material. This is basically like a recipe for how many components you need to take of each type of a component to assemble a product. Then we have a component supply, so what we get from our suppliers. We have a demand for products from customers. We have capacities of factories because, well, it's not infinite, and also sometimes factories are going through some downtime to maintain and check their production lines. Further, we have products interdependencies. What's that? This is when the customer is ordering certain products, and there's one order and, for example, 3 products, they want these products to be delivered together. And so it doesn't make sense for them to get only one item out of that. They want all together. So these are these interdependencies. These are basically given by the order. And finally, we have net unit price of each product. So how much do our customers pay for each product? Further, we have decision variables. And the most important decision variable here is Y, meaning the fulfilled demand. So how much demand out of this customer's demand did we manage to fulfill? We have a complementary variable being a complement of this Y, and this is unsatisfied demand. So we need to keep track of both. And finally, we have X, and this is the number of components that we used to manufacture these products that are manufactured in Y. So X is kind of very much dependent on Y, and you can see Y as the only decision variable. X is given by the bill of material multiplied by Y, but for sake of ease of use, we are keeping track of all these variables. And the objective we have is to maximize the revenue. So basically the revenue is number of items, number of products multiplied by the price, and we do it for every product and every customer. Further, we have some constraints. So we cannot use more components that we have supplied from our suppliers. Then we cannot, we are not really interested in exceeding the demand. So this is also a constraint that we don't want this to be exceeded. Further, we want this satisfied and unsatisfied demand together to be very close to the demand from our customers. So actually, this is the level of demand that we want to control. Further, we cannot exceed the factory's capacity, so this is also captured. And we want to maintain these interdependencies, so that's captured as well. And finally, we have non-negativity of our variables, because it doesn't make sense to produce the negative number of products, as well as it doesn't make sense to use the negative number of components. Also, which comes from integer linear programming problem, we have these variables integer. And at this point, I should explain to you what is integer linear programming problem. So, as I said, these variables are integers. So integer corresponds to the decision variable. And, well, again, it doesn't make sense to buy 7.2 capacitor or 2.7 resistor. Not really. These are integer numbers. So we can buy 7 capacitors, 2 resistors, or some other number, but it needs to be integer. So this is where integer goes. Now, linear. Linear corresponds to the objective function. And so, well, it basically means that our objective function is either a line in 2 dimensions or a surface in 3 dimensions on an n-dimensional equivalent of a line in n dimensions if we happen to have n variables. And programming is the most confusing, because programming is a synonym of optimization problem. Programming was used in this context in the 50s of the previous century, when the programming as we know today, meaning programming languages and software engineering, this didn't exist yet. And so to the person who coined this term, optimization problem seemed like a program, like you give the things like variables, objective, constraints, seemed like a program. And so the term was coined, and it survived until today and is still used. But it means no more than optimization problem. Okay, so that was the formal definition of optimization engine that is the key of a presentation today. Let us now look at some examples. So we are dealing with some key toy example where we have several products, several components, and several customers. So it's like 9, 8, and 20 of each. At the bottom chart, we have demand for each of the products. And so you can see how that varies in time, because we are covering here 12 periods, 12 time periods. And so the use cases in which the optimization framework that we developed can be used are, first of all, open market purchase recommendations. So this is something that I mentioned already. When you can buy components in an open market, but you don't know whether it pays off. So this is where we can make this kind of recommendation whether to go with such a purchase or not. The second use case is benchmarking strategic factors. So first, maybe for some reason you want to, or your company wants to focus on a certain market because it's strategically very important. Like, no matter how much it costs, you just want them to be happy because you want your company to grow in this particular region or to monopolize this region. And that comes usually at a price. It's usually not optimal in case of component shortage. But the question here is, how much does it cost? Okay, so let's look into these use cases in more details. So first of all, the use case of open market purchase recommendation. And so here we have the situation. In a top chart, we have we have a situation with components. So as long as it's yellow is good, but as soon as it gets more diverse colors, we can see that there's a shortage of this particular component. So here we are missing 3 components. These 3 components are actually contributing to 4 products and are purchased or ordered by several customers. And what we want to do is to assess whether buying any of these components in an open market is worth it. And so we are considering the open market purchase at 20 times the median wholesale price, so 20 times more than we would pay to our regular suppliers. And now the stakeholders might be asking, will buying component 8 alone increase the production output? Or they might be asking, will buying component 2 and component 4 together will increase the production output? And let's consider the case of a component 8 alone only. So here in the charts, we are looking at the quantities that are being manufactured and the net sales that is being produced out of this of these components, of these products. And as a baseline, we have a darker line. So this is the regular component optimization without any additional purchases. This is what we can get without asking anyone for help, external help. And as you can see, the pink line, which is the situation after we purchase this component 8, is exactly the same as the benchmark. So buying component 8 alone did not unblock the production. So we basically wasted money. On the other hand, if we buy component 2 and component 4 together, then we can see that this pink line goes above the baseline, meaning that first of all, we were able to produce more products, and second of all, we got more revenue out of it. And to summarize, if you just go with component 8, you will waste money on purchasing these components, and you will not get any value out of it. On the other hand, going with buying together component 2 and component 4 is increasing the revenue quite significantly. And this kind of answer we can give to our stakeholders so that they can make wise decisions or informed decisions at least. Now let's look in a second use case. So here we are benchmarking these strategic factors. Benchmarking whether prioritizing certain customers, how much does it cost basically. And here our situation is a little bit different. So we are missing just one component, but this component is used by 2 products, and these 2 products are purchased by 2 different customers. As you can notice, one customer is paying quite a lot of money for the products they are purchasing, whereas the other is paying very little. And so now we are using a little bit modified objective function. Because what we are doing, we want to maximize the revenue, but on the right-hand side, we have revenue of all the customers multiplied by some small factor alpha. So we still want to monitor them, but we don't care too much about them. And the first element of the objective function equation is actually just over the customers that we want to prioritize. And so now the stakeholders might be asking, how much does it cost to prioritize customer 16? So this is the one who is paying very little for the product they are ordering. And so now let's give them the answer. So first of all, looking at the quantities that we are able to manufacture, these quantities are basically the same which you get by the height of the striped rectangles in a plot. It's only that instead of manufacturing one product, we shifted to another product. And so now we are not producing the product for the customer who is paying a lot. Instead, we are producing the product that is ordered by customer 16. When it comes to revenue, the differences are more substantial. So you can basically see that the revenue that we got now from these yellow bars, this is very low comparing to what we were able to obtain previously from the other customer. So in total, the cost of prioritizing certain customer can be evaluated this way by comparing to the benchmark scenario. And here the benchmark scenario is always this regular revenue maximization that we do without any additional purchases or without any any additional prioritizations. And that way we can give a cost that, for example, in this situation, if we wanted to prioritize customer 16, it costs 1.2 million euro. So that was about the algorithm itself. Now the second part that I promised, which is embedding this solution in the cloud. And that's a little bit less mathematical, so if you fell asleep, you can now wake up. And why is it important? Well, first of all, the great majority of projects of artificial intelligence models never make it into productions. The 87% or 90%, depending on the source, but it's a great majority. And secondly, it is actually critically important when we develop such a model and it's giving us the answers to some very difficult question, then it should be deployed and available to the user so that they can make use of it and solve the problems that they are facing. And the modern architecture that or the modern ecosystem or environment in which we are embedding our applications is a cloud. It might be changing, like obviously it is changing. 10 years ago it was in on-premise infrastructure, today it is cloud. Tomorrow it might be something completely different, but what is important is that we want to embed the this model that we built into the infrastructure that is currently modern, used, and will be made use of. And so the major reasons why we move towards cloud is first of all, it is due to the decrease of the cost, due to scalability, due to business continuity, or due to collaboration efficiency, because everyone can have access to this cloud environment, due to flexibility of getting one service, switching the other service off, and so on, and also due to fashion. So there's this ongoing trend of deploying business solutions into the cloud environment. And when we look at the architecture of the solution that we proposed and what we developed, let's first have a look at the ETL process. So here we basically have on the right-hand side there's this MATLAB, Azure MATLAB VM. This is the virtual machine on which the MATLAB program is deployed, and the whole optimization engine was written in MATLAB. It is using the optimization solver. This is a commercial one, but the problem was defined in MATLAB. So this is like the core of final architecture. And let us now first focus on this right-hand side, because here clearly we have two sides of a picture. Firstly, we have this weekly data processing that is mostly concerned with data update. And on the right-hand side, we have case data processing, which is basically incoming parameters from end users who want some scenarios calculated for them. So here from the architecture perspective, we have a user who accesses our application via front end. And they put in some parameters, like what kind of objective they want, whether they want to prioritize certain customers, whether they purchase some components, all these kind of parameters. These parameters are then passed into some web API that communicates over the service bus and executes a console application that in turn executes MATLAB, which is a little bit executing chain, but nevertheless, this is where the whole parameters are passed to MATLAB, and the MATLAB is doing the heavy lifting. Now the results are passed back, stored in a database, and that database, and also the data coming from the ETL process with a weekly update, this is then fed into Power BI, that again is displayed to the user. So it's kind of like a loop process, and every scenario that is being calculated is actually enriching the whole data that is in the system. This is from the application point of view, like the backend architecture, and that actually doesn't look like rocket science. And but let us now look at this weekly data processing. Here we again don't have very much of a rocket science. Actually, there's this rocket science is after all is nowhere. It's mostly about software engineering skills to put and the DevOps skills to put these things all together. But here within the weekly data processing, we actually wanted to achieve certain thing. We wanted to have this whole data processing part done automatically without any need of human labor. And this is where the challenge came in. So this wasn't about the whole architecture of the solution. It was about these elements here and there that were detrimental to the whole process, or were actually obstacles that we needed to overcome. And especially there was one database. I mean, it is noted here as a database, but it's actually a data source. And automating this data source became a great challenge to us. And how we overcome it, I'll describe in the automation part. And well, let us jump into it. So the challenge itself, it was arising from the fact that we were using Windows desktop application to get some data. This desktop application was a top-notch solution like 10 or 15 years ago when it was purchased. But unfortunately, it isn't in development mode anymore. It is only in the maintenance mode. So if some bugs happen, then somebody will fix them. But otherwise, sorry, no. And the unfortunate part of it was that there was no web API to get the data. There was no direct connection to the data warehouse or whatsoever. And the only way to get the data out of the system was by manual clicking and waiting. And for a person to do the export of all the reports that we had designed, it was taking 1 hour. And now imagine we would have to do it every week. So 1 hour of clicking and waiting. So, well, you can think of better things to do at work. At least I can. This was the challenge that we wanted to overcome. And the way we did it was with E2D2. E2D2 is a bot that is doing this clicking and waiting for us. And so here's a little bit of an architecture of how that E2D2 looks like and how it worked. And so on the left-hand side, we have the virtual machine. And on the right-hand side, we have additional Azure services in the cloud. And so every week, on this virtual machine, Python script was executed. And this Python script was executing or starting this desktop application that I just mentioned. Because this application, well, it was protecting the data, so it requires some multi-factor authentication to get to it. So first of all, we needed the user and a password. And then we needed some additional information. Here exactly it was cache token to perform this multi-step authentication. And so this data is kept securely in a key vault in Azure cloud. And so once we obtained this data from the key vault, we were able to log in into the application. And after the login, the application itself was sending some sort of one-time password to the email associated to the user that we used. So using the cache token, we were able to access the email and read this one-time password. That allowed us to authenticate. And at this point, actually, the reminder of the whole bot was relatively easy because there exist tools to our libraries to click on a desktop application, and so in a loop we were able to extract the reports out of this application. And finally, once the export was done, the whole bunch of files was copied to file share. And did it solve a problem? Well, yes. Did it exclude the manual labor? Almost. So if you have multi-factor authentication, then basically you, well, probably from a security point of view, you shouldn't be overcoming it fully with a machine. So there need to be still a human in a loop. But then the amount of work that is required to be done is very tiny. It's just authenticating and refreshing the token every now and again. So why did I talk about it? To just make you aware that, or maybe you are aware of it already, and probably you are. But I wanted to stress the fact that when it comes to designing the overall architecture of a solution, from my point of view, it is not that difficult. The difficult parts are these elements that are like obstacles that are preventing us, for some reason, like this desktop application, from automating fully our workload or our workflow. And these challenges are kind of fun to resolve, and for me, working on E2D2 was definitely a fun. So yes, conquering these small challenges is actually making a difference. And now let's move to the summary. It's time for us to slowly finish this presentation. And so let's recap on what I talked about. So, well, this presentation was about this artificial intelligence-based solution that works end-to-end and is able to provide some insights to the users to allow them to make informed decisions. So, going from the bottom layer, we have a human, the user, who wants to answer certain question. They can access the application through the user interface that passes on the data, enriches this data with what we already know about the world, so to say. This data is fed into the optimization algorithm, which in turn is producing some results. These results are presented in a Power BI, embedded in a web application, and that allows the end users to make some insights and make these decisions that they were after. So this is the overview of the application on a kind of use case level. But to finalize and conclude the presentation, I think there are two aspects of a successful business solution. So first of all, the solution needs to pinpoint and relieve the pain of stakeholders. And secondly, it needs to be embedded in a modern infrastructure so that it can be used by the stakeholders easily. And so when it comes to our application that we developed, well, it's basically fulfilling both these requirements or both these aspects. So we addressed the problem that was a pain to the stakeholders, to business stakeholders at the company. We used some state-of-the-art research methods to solve this problem. Then we were able to embed the solution into the modern architecture, modern infrastructure, meaning the cloud. And finally, the solution is already used by the stakeholders and is generating financial impact. Thank you for your listening.
Agata, thank you so much. Thank you very much for this analysis. Cheers. This is Code Dive. Don't go away. We'll be back after this break.